Planet Earth, the special planet. Key features distinguishing Earth from other planets. Its atmosphere is mainly made up of oxygen and nitrogen, the presence of liquid water covering around 70% of the surface, and it contains life in both simple and complex forms. Planet Earth, spherical. Evidence that the Earth is spherical. Ships don't fall off the edge and disappear over the horizon. Satellites orbit Earth. This would be impossible if it was flat. The curvature of the Earth's shadow can be seen during a partial lunar eclipse. Aircraft fly in arcs rather than straight lines, the shortest distance over a curved surface. And images of Earth from space, showing it is spherical. Planet Earth, latitude. The angle between a point on the Earth's surface, the centre of the Earth, and a point on the equator is called the latitude of that point. It is expressed as an angle in degrees north or south of the equator. E.g., the latitude of Edinburgh is 56 degrees north, and Buenos Aires is 35 degrees south. The poles have latitudes of 90 degrees north and 90 degrees south. Planet Earth, axis and equator. The Earth's polar axis is tilted by 66.5 degrees to the plane on which it orbits the Sun, the ecliptic. Therefore, the Sun only lies directly above the equator on 2 dates every year, the spring and autumnal equinoxes on the 21st of March and the 22nd or 23rd of September, respectively. Between these dates, the Sun resides over different latitudes of up to 23.5 degrees, the tropics of Cancer and Capricorn, on June 21st and December 21st, the summer and winter solstices. Planet Earth, longitude. The longitude of a point on the Earth's surface is the angular displacement east or west of the observer's meridian, an imaginary north-south line running through the point, from the prime meridian, which passes through Greenwich, London. Longitude is also expressed as an angle east or west of the prime meridian, e.g. Sydney is 151 degrees east. The meridian of an observer can also be visualised by an imaginary plane that meets the observer at a tangent to the Earth's surface. This can be visualised as an imaginary line along which the sky meets the land, or sea. Planet Earth, light pollution. Sky glow is light pollution which hinders observations of the night sky. Light shines up into the night sky, causing an orange background haze, covering faint stars, nebulae, and the Milky Way. The main sources of terrestrial light pollution are floodlights, street and motorway lamps, domestic and industrial street lamps, and lights above car parks and shopping centres. The British Astronomical Association's Campaign for Dark Skies, CFDS, was set up in 1989. It campaigns against excessive, inefficient, and irresponsible lighting. They work to persuade local authorities about benefits of well-directed lighting. Planet Earth, Eratosthenes. He was a Greek geographer and mathematician in the 3rd century BC, and performed the first accurate determination of the circumference of the Earth. He read that at noon on summer solstice in Syene, the sun lay directly over a well. Also, columns on temples did not cast shadows. Syene was on the Tropic of Cancer. Measurements of the sun on the same day in Alexandria showed it was 7 degrees from the zenith, almost 1/50th of a circle. He learned that Syene was 790 kilometres further south than Alexandria, so he used simple geometry to deduce the circumference of Earth was 50 times this value, i.e. 39,500 kilometres, which was within 5% of the actual circumference. Planet Earth, Eratosthenes' problems. Syene was not quite on the Tropic of Cancer, there was uncertainty in the distance from Alexandria to Syene, and the unit of measurement used by Eratosthenes and its conversion into kilometres. Planet Earth, atmosphere. Our atmosphere contains a mixture of gases. By volume, the main constituents are nitrogen 78%, oxygen 21%, argon 1%, and CO2 0.04%, and an average of 1% water vapour. With increasing elevation, the atmosphere becomes thinner, gradually merging with outer space at an altitude of about 10,000 kilometres. There is no uniformly accepted height that defines the boundary between the top of the atmosphere and space. Astronauts usually agree on a value of 100 kilometres, a boundary known as the Kármán line. Planet Earth, atmosphere's benefits. It absorbs harmful solar radiation, ultraviolet, that can cause accelerated skin aging and skin cancer. Absorbs harmful energetic X-rays and gamma rays from space and prevents them reaching the ground. Regulates the temperature so we rarely experience extremes. Provides us with oxygen to breathe, and partly protects us from meteoroids. The majority burn up as they pass before reaching the ground. Planet Earth. Atmosphere costs. The reflection of light as it passes through our turbulent atmosphere, causing stars to twinkle and restricting the resolution of an image. The selective scattering of shorter, bluer wavelengths of sunlight by gas molecules in the atmosphere, making the sky appear blue and preventing observations during the day. The absorption and reflection of the majority of electromagnetic radiation from space, preventing most wavelengths from reaching sea level and requiring most ultraviolet, X-ray and gamma-ray observatories to be on Earth-orbiting satellites. Planet Earth. Atmosphere and radiation. The longest radio waves are reflected back into space by electrons in the ionosphere. Some short wavelength microwaves are absorbed by water vapour and oxygen. Most infrared, IR, radiation is absorbed by water vapour, CO2 and methane. Ultraviolet radiation is absorbed by ozone and, at shorter wavelengths, oxygen. X-rays and gamma rays are absorbed by oxygen and nitrogen. X-rays ionize atoms and molecules, and gamma rays excite their nuclei. Either way, the radiation loses energy and fails to penetrate much of the upper atmosphere. Planet Earth. Telescopes. Telescopes collect light and produce a focused image that can be viewed, studied, photographed, or analysed. Refractors. A glass convex lens collects light and brings it to a focus. Reflectors. A curved mirror, or one made from several segments, collects the light. The lens or mirror is called the objective, and the size of a telescope refers to its diameter. Planet Earth. Telescope comparisons. Larger telescopes are better than smaller ones because they collect more light and have higher resolution. Most professional telescopes are reflectors. This is because large mirrors can be manufactured to a much higher precision than lenses that are heavy and difficult to support. Planet Earth. Observatories. To find an ideal observing site, consider atmospheric properties, e.g. cloud cover, air turbulence, sky brightness, and water vapour content. Also consider geographical location, e.g. access, utilities, likelihood of earthquakes, and ground stability. For mainly the first reason, most optical and infrared observatories are located on mountain tops, such as Mauna Kea in Hawaii. Planet Earth. Space satellite advantages. There is no atmosphere to blur images or reduce resolution. There's no light pollution. There are no adverse weather problems. Longer observing periods, darkness. And there is the ability to detect other wavelengths, in particular gamma rays, X-rays, and far IR, longer wavelengths. Planet Earth. Space satellite drawbacks. They have a shorter lifetime than those on Earth. It is difficult or impossible to maintain, repair, or upgrade them, and they are extremely expensive, both to build and to launch into orbit. Planet Earth. Van Allen belts. They are radiation belts surrounding Earth. There are two, the inner and outer. They are made up of high-energy particles and are held in place by the Earth's magnetic field around its equatorial plane. They are byproducts of cosmic radiation. This is the cooled remnant of the hot Big Bang that fills the entire universe and can be observed today with an average temperature of about 2.725 Kelvin. The Sun, Jupiter, and Saturn are also encircled by radiation belts similar to Van Allen's. This is because radiation belts can exist around any body that has a magnetic field strong enough to keep the charged particles in place. Planet Earth. Van Allen belt's discovery. Explorer 1 discovered the inner Van Allen belt in January 1958. It was unexpected, as it had originally been sent to measure the intensity of cosmic rays. The belt was detected by a Geiger counter aboard the satellite. This was confirmed by Explorer 3 and Sputnik 3. Pioneer 3 discovered the outer Van Allen belt in December 1958. Its original use was as a lunar flyby. Unfortunately, the launch vehicle's main booster engine experienced a fuel cutout, meaning the spacecraft only reached an altitude of 100,000 kilometers. As it fell back to Earth, its Geiger counters produced data which meant Van Allen's team could detect the outer belt. This was recorded before it burned up during re-entry. Planet Earth, inner Van Allen belt. Very dense and compact, and is mainly made of high-energy protons. These are created when atoms in the Earth's atmosphere and cosmic rays collide. Fairly low altitude at 600 to 10,000 kilometers. Therefore, scientific instruments and astronauts and satellites can be at risk from prolonged exposure to its radiation. Intensity varies but is strongest at 2 to 5,000 kilometers. This is influenced by the Sun's solar cycle. It is nearest to Earth at the South Atlantic anomaly, 200 kilometers. Planet Earth, outer Van Allen belt. Much more diffuse and dynamic than the inner, mainly made of electrons but also from other charged particles emitted from the Sun as a result of solar activity. Much wider than the inner and dips sharply at the Earth's magnetic poles, sometimes known as its horns. It is surrounded by a region of low intensity known as the ring current.